Welcome everybody to the SOLARX webinar. We are organizing this webinar today, 9th of June, because some leaders of 6 European funded projects will explore the challenge of deploying innovative, fully dispatchable hybrid renewable technologies based on solar concentration. The webinar title today is Solar Concentration Technologies for Flexibility on the Production Side, and it will be hosted by the SOLARX project. This is a webinar that aims to give you an overview of what's going on the concentration solar power, but also in many other technical and non-technical challenges that we are discussing with the different projects related with SOLARX. First, I wanted to share with you some housekeeping. This event will be recorded and some highlights will be shared later on in the SOLARX website and the other projects' social media channels. And you can always ask questions. If you have technical issues, you can write in the chat and we will answer it as soon as possible. And if you have more technical questions about the discussions that the experts are sharing and so on, or questions about the projects, you can use the Q&A function. And after the presentation, if the speaker want to answer any of the questions raised, they will be happy to do so. So this is the overview and the program that we have today. I am Miriam Frances from Axelopment, and I am organizing the latest webinar because we already organized a couple of them about these topics. And today we have the pleasure of having not only the SOLARX partners, but also other 5 projects that are developing and working on the same field. So today we'll start Jerome himself. He's the project coordinator of SOLARX from University of Lleida. And then we will have another speaker called Nicolo Cairo from ETM Global, and he is leading the Robinson project. After him, Fritz Sabersky from CENER will speak about the Asterix KSR project, another EU-funded project in the field. And then from Hybrid Plus, we have Cristina Prieto. She is from the University of Sevilla, and she will also showcase the things that they are developing into the project. After her, Enrique, he is also part of SOLARX, but Enrique Pascual is also part of the coordination of Leia, because Acciona is the coordinator of this project. And to finish, CST for all, we have Peter Heller, and he will also share the latest insights about this project. But I will not extend myself again. I will share this screenshot to share you a little bit the main title and topics of each of the projects. But I think the experts today will explain them much better. So yeah, Jerome, I will give you the floor. Thanks again for hosting this webinar as a SOLARX project coordinator. And I will stop sharing so that you can have the option to explain about the SOLARX concept and the status of the project.
Okay, thank you, Miriam. Okay. Okay, I hope you can see it.
Yes, we can see your screen.
Okay, thank you. So thanks, Miriam, and thanks everybody for joining, all the speakers, but also the assistants. So I'm John Burr from University of Lleida, and I will present our SOLARX project within this framework of this webinar about solar concentration technologies for flexibility on the production side. So SOLARX is the project that is called dispatchable concentrated solar twix energy solution for high penetration of renewable energy, and that's how I will present the context of this project, the main concept, and some preliminary results also. So SOLARX is research and innovation action, so quite a low TRL level. We want to reach TRL 3-4 at the end of the project. At the end of the project, so it's a call from cluster 5 for energy, and the end of the project is in October of this year. So we are right now trying to extract the main conclusions of our all the work that has been done, and I will give you some insights. The project is the consortium is composed by 9 partners from 7 countries, 5 research institutions, 3 SMEs, and 1 industrial partner. And so here some words about the context, because that's something that can be also useful for the rest of the projects. So we are all trying to work for a more renewable energy system, and so our goals are likely to be common between all the projects. So just a few words. Most of you already know it, but from the International Energy Agency, we can see this stat from last year. Basically, we know that renewables are increasing into the energy mix, and even more in the electricity mix, but in the energy mix in general, they are increasing very fast. But they are increasing through technologies that are intermittent, so non-flexible, and without a capability of dispatch the energy. As we can see here, most of the growth of the share of the renewable energy systems is from solar PV and wind power. So we only produce when we have this resource available. And in the framework of the ambitious goals, we can say ambitious right now when we see how we advance. But for example, for the net zero emissions by 2050 scenario, of course, we need to increase even more the share of renewable energy systems into the energy mix, and that leads to some issues that we have seen in the last weeks. A few words about this energy transition. So we want to move from a system with a baseload production and to match the energy demand along the pointer to match the energy load along the days. Of course, we have to bridge the gap here between this demand and the base load, nuclear, non-dispatchable renewable energy systems, and others. And basically, right now, what we do is using fossil fuel technologies in order to provide this energy to fill this gap. And so in the transition, the objective is to move from this scenario to a scenario where we can combine some variable renewables like PV or wind power with dispatchable renewables. That would be the best to reach the net zero emission goals in 2050. So move. And some other insights from the last months and last weeks that we could detect these tendencies. We need more flexibility also to fight some additional problems of the energy system right now. One is the price cannibalization. We know, for example, in Spain and in many countries, when there's sun, the price drops down very quickly, and so we reach a high number of hours with zero prices or negative prices for example, for the electricity. Here we can see in the growth in different countries or zones of Europe, the growth of this number of hours with negative prices. In the last 2 years, it has increased very, very quickly, but also just as an insight, in 2025, in the period that we have already passed in 2025, we have even more hours of negative prices than in the entire 2024. So really, this number of hours with negative prices is increasing very fast, and that's a problem for the economical reliability of renewable energy systems. Another issue in terms of efficiency of the grid is also the curtailment. Curtailment is increasing very fast in all the countries of the world. But for example, in Spain, it's expected 5% of curtailment in 2027-28. So it's an inefficiency that we should try to fight also. So now I will present quickly the concept of SOLARX. SOLARX is a central tower system, concentration system. So we have an heliostat field, like in conventional CSP, and the central tower, in which in conventional CSP system we have a CSP receiver to produce vapor and then turbine it to produce electricity. In this case, we have this similar heliostat field that is sized in order to be able to fit into 3 receivers that are at the top of the tower. So a CST receiver, in this case, we don't have any additional developments. We take the data from our industrial partner, Acciona, but also a hydrogen receiver, some micro reactor that can use biogas, and that are able to produce hydrogen from the solar energy source, but also through the use of potentially curtailed electricity from the grid, so helping to stabilize the grid with high efficiency in the conversion, and also the adoption of some carbon capture and use strategies. So this is for the hydrogen receiver, and finally an electricity receiver, a CPV receiver. In this case, what we want is to have a receiver that is able to produce electricity at a given moment with a very high efficiency. So here we work on the solar cell, but also on the entire receiver in order to maximize the efficiency of the entire receiver. So the CPV and the hydrogen receiver are 2 of our technological elements. The other one is the management of the heliostat field, because here really what makes the difference is the capacity to decide on which receivers we send the solar resource at each moment. And here the criteria can be technical, but really what matters more is the economical criteria. And so within the algorithm to decide what we do with the solar resource, we take into so what we have as the storage levels we have for the different energy vectors. And it is very important, the real-time energy demands and markets. Price is very low or negative. Okay, so in this case, we show some examples. We will take other options. And finally, end users. So for electricity, residential, commercial, industrial customers, also be able to provide some ancillary service and synthetic fuels. So we can have also other kind of receivers on the towers, and also can be useful for metallurgic and other industries. And the heat we can use for solar heat for industrial processes, a conventional CSP plant, or district heating and cooling. So all that is assessed in a techno-economic way, environmental and social way. of this project, the smart sources, solar resource management, the CPV then solar receiver with a huge work on by Seniors on the cell efficiency, and also by UDL on trying to reduce the gap between what is the efficiency of a single cell and what is the efficiency of the entire CPV receiver. So we have some mismatch losses and pumping power to cool the system, and we want to reduce at the minimum, and so to have a lowest difference between the CPV cell efficiency and the CPV receiver efficiency. And finally, the B energy, so solar and electricity, hydrogen solar microreactors, compatible with biogas, and being able to integrate carbon capture and strategy and storage strategies in order to provide low carbon or even carbon negative operation for this receiver. So all this is integrated in this way. So we have the frequencies, also the data for the CST receiver. We integrate all of them in a technical model, and together with the different inputs that can be the demand scenarios, the system costs and regulatory frameworks, we obtain and validate the SOLARX performance in different scenarios and locations. And also, and more important, we integrate all this data into an economic model in order to assess which is reliability and the impact that can have the SOLARX concept in future implementation strategies. So to resume the aim of an objective, so we want to integrate and make a synergetic management in a single facility of a system that produces heat, electricity, and hydrogen with high efficiency and depending on demand and price. So to be able to demonstrate the dispatchability and flexibility of this system and how it impacts on the maximization of the owner benefits, important to make it attractive for the investors, and also how we can provide ancillary services to be able to help to stabilize the grid. So make a solution attractive for investors, grid operators, industries, and citizens, and being an agent of this green transition to high range penetration scenarios. So, as I said, different scenarios. I will not enter more in detail, but just 3 types of applications. This is important. General applications, so to feed the grids, the different grids for each of the energy vectors, but also an industry application. In this case, what we want is to match the demands of a given industry. And islands, here the main objective is to decarbonize the island. So these are those 3 cases that we are studying with different locations in Europe, and we compare with different technologies as a function of the type of application, with different KPIs, LCOE, of course, internal return rate, but also COVI. COVI is the cost of valued energy, and this is a very important factor for flexible and dispatchable systems, as it takes into account at the price of selling each of the energy vectors at any time. Okay, so taking into account the variation of prices of energy vectors that we produce. Okay, just move forward. Some examples. So these are examples. This is a simple example in this case, with only 2 receivers on the top of the tower: thermal receiver, CST receiver, and CPV receiver. So we can produce directly electricity or store the heat and produce electricity later to feed the grid. This is a model of Energy Pro, a commercial program from EMD, a partner of the project, but we also did the same systems with high design and open source software from DTU in Denmark also. And we validate both models with these simple cases. And in this case, some quick results and also how it behaves in order to understand the operation of this kind of system. So we have here the direct normal radiance, so part of the solar radiation that we can use in concentration systems. The spot prices in Spain, in this case, in 2023, and here it's for 3 days of July and August 2023. We can see here that when the prices are relatively high, we use a CPV receiver in order to produce electricity at high efficiency. But when the price drops down, it makes more sense to not fully use the CPV receiver, but also send part of the solar radiation on the CST receiver in order to store energy. We can see here how we store the energy, and when we have higher prices in the afternoon, we use this stored energy in order to produce electricity here. So here, of course, we need, for each case, application and location, we have to optimize the sizing of each of the components. For example, the nominal power of the CPV receiver, the nominal power of the CST of the steam turbine, but also how much energy can we store into our storage system for heat storage system. So we have to play with a high number of parameters in order to optimize the sizing of the entire facility. And a very quick data here, main result, the COVID reduction by 31% was compared with CSP for this simple configuration in Spain. So an interesting impact in this case for owners. Also, so I don't have a lot of time now, so very quickly, we have already validated the model for the free receiver with the different inputs for the hydrogen receivers, in this case with the biogas water, not to produce the hydrogen. And another application that we think it's very important also, apart from Iceland, that we did not already implemented, but another one is for industry application. So in this case, it's only CPV and CST receivers, but this is not to feed electricity into the grid, but this is to match energy demands from an industry that we have here nearby Lleida. So just to finish, as a conclusion, flexibility is a must right now. We saw it in the last weeks in Spain. Flexibility on the production side needs to be further explored. There are some a lot of publications on flexibility on the demand side, some change in the regulation in some countries relative to this flexibility on the demand side, but really flexibility on the production side is also important to be able to stabilize the grid and allow to have an increased share of renewable energy without a lot of curtailment and without inefficiencies in this case. So okay, so important for the net zero emission goals, for potentially increase also the non-flexible, the intermittent renewable energy systems. If we have systems that are able to provide this flexibility and dispatchability, we can also increase the number of systems that do not provide this kind of capacities. Can be important for the grid stability and for the economic reliability of the system, as we are able to tailor the production of each of the energy vectors to the prices of these energy vectors in the market at each moment. So thank you, and if you have some questions, so you can send us any email or put them here in the Q&A section, and we'll try to answer. Also, I invite you to follow our website and our communication channels in order to be able to receive in short, because the project is nearly at the end, the main result for this kind of application that I was showing you here right now at the end of the presentation. So thank you. I try to finish the share. Okay.
Yes, so now it's time for Robinson. Nicolo, you can start sharing your slides and
Yes. Can you enable again the video? Okay, good. Thanks. So I'm just sharing my screen. Very brief. Can you see the screen now with Robinson?
yes, we see it
Good.
perfectly.
Thanks. So, Robinson. So our project was launched in September 2020 and it is part of the Horizon 2020 program. And it aims at decarbonizing industrial islands in different geographical contexts. So with the integration of technologies that are already existing or are new to the market, with the aim of serving or providing both electricity, heat, and gas. The demonstration of Robinson, because our project aims at TRL 7, so the demonstration of the system is currently being carried out in Egerøy, an island in Norway, along with some virtual demonstrations both in Crete and also Scotland in Western Isles. What you see here is some basic information about our project. So we are a large consortium of 18 partners from 10 different countries with the expected finishing date of the project in June 2025, so 3 weeks from now. What we aim with this project is the development of an integrated energy system with a flexible and modelable system that can provide some dispatchable energy. In doing so, we couple available energy sources, like available locally, in order also to increase energy efficiency, security of supply, and also reducing emission of greenhouse emissions. So in order to meet the requirements of the energy trilemma. And also, of course, reducing the use of fossil fuels, especially in industrial applications. What you see here is the plan concept of Robinson. In a nutshell, the PVs is an essential part of the system itself. That was originally foreseen to play a key role in providing energy both for the industry but also for the households. However, what you see in the next slide is some changes within Robinson. Last year, we installed wind turbines and PVs, not in Egerøy in Norway. However, we installed them respectively in Greece and in Germany, so to demonstrate the capability and the performance of the technologies itself. Moreover, we did not install any gasification unit and district heating system in the demonstration plant in Egerøy, but this is a very positive outcome for our project, we installed a large electrolyzer for the production of hydrogen. So as we are approaching the end of the project, we would like to share some key results with you. So how did we have this change in the planning of Robinson? Well, we could say two main reasons were the driver for these changes. On the one hand, we had public resistance. So we had politically driven decisions that prohibited the installation of wind turbines. So there was not a consistent or a solid social acceptance for the installation of this technology. And moreover, we had a more important driver here, which was energy prices. So this also prohibited the installation of the gasification unit. And in a nutshell, our learning is that decarbonization is always driven by a business model. And if this is not solid enough, the planning, the original planning for the decarbonization may be severely affected. Now, what we also had in terms of challenges and also lessons learned is that in Europe, because we had 3 different countries for the demonstration, right? We also experienced different rules and regulations. So for instance, regulations for the installation of wind turbines was significantly different between Scotland on the one hand and Norway on the other hand. Also, the stakeholders, as I just mentioned, expressed their own resistance regarding the installation of certain technologies, and also they were not fully convinced about the benefits they could get as part of the delivery of these technologies. However, what we can deliver, what we did have achieved in this project is the development of an alternative integration system that is currently being demonstrated in Egeroy, especially with the new energy management system, and also the development of business case models that have been developed by Strategen. Not only this, one of the Robinson project objectives that we would like to present today at the webinar is how we achieved the replicability of the modular energy management system. One of the original objectives of Robinson was to demonstrate the replicability and also to develop 2 tools that could be used by municipalities and geographical islands, so to develop their own energy management system. To do so, the Robinson project, led by this effort led by the Technical University of Crete, developed the web evidence-based. So this is a web platform where you can find, when one can find all the knowledge and data developed during the project, both at the technological and also legal and societal acceptance point of view, in order to enhance the upscale and uptake of technological solutions. This serves the purpose of supporting the decision makers in developing a suitable and appropriate deprecation plan that fits the specific geographical needs. In doing so, the web evidence-based also includes a roadmap tool that includes a 6-stage proposal that has to be carried out in order to ensure a successful replication, starting from the analysis of the requirements up to the demonstration of the plan itself. What you see here is that this platform of the replication hence includes the roadmap database, the tool database, and the knowledge database. Out of this, we developed a roadmap tool overview. What you are going to see now in 6 steps is, on the one hand, the guides replication that the Technical University of Crete developed for Crete and Western Isles, which were the virtual demonstration sites. It also includes a specific adaptation in terms of energy potential, infrastructure, and regulation for each of these islands, and also includes business models planning for energy communities. So the replication roadmap tool of Robinson is shown here. So we do have on our website a replication tool that always starts by the identification of the needs and potential for each of the geographical islands or decentralized energy systems, followed by an action group, so the stakeholders, the relevant stakeholders gathering together, supporting an action for the decarbonization of an island, the development of a technical solution, followed by the application context. So this is also to include the analysis not only of the technology but also the societal acceptance and the regulation in place in a certain country, followed lately by the adaptations that have to be implemented for each context, and finally the implementation and the testing of a complex energy management system. So in a nutshell, and here I bring to the conclusion, the Robinson system is on the one hand a very good example of how decarbonization is really more complex than we are used to think about, because it is, from our experience, it is really driven by business models. But on the other hand, we also provide a scheme for the replication of our tools, of our systems for the different geographical islands that are already online. So our project will finish in 3 weeks from now. And this is what we bring to the society, what we bring to other European countries is a solid base to further strengthen the development of energy management systems and get to TRL 9 for the decarbonization of geographical islands. So here was my last slide. And here you also find the Robinson website as well as the info@robinsonh2020.eu. So wherever you have any questions, please feel free to contact us and we'll revert back to you accordingly. Thank you very much.
Thank you, Nicolo. Very interesting presentation. Now I think we don't have still questions from the audience, but if you want to ask something later on to Nicolo, you can also drop a line in the Q&A session and we will be happy to provide to him the question to answer. So now it's time for Fritz, if I am not mistaken, Fritz Saversky from CENER.
Yes.
Give you the rights.
I'm going to share my screen. Can I say something?
We hear you.
Can you?
We can hear you, but we cannot see your screen.
No.
Now it's working. It's, yeah.
Okay. Now it's working?
Yes. Perfect.
Yeah.
Proceed.
Perfect. Okay. Hello, everybody. I'm going to present the SOLARX CISA project. And the SOLARX CISA project is a combination of concentrated solar power, concentrated solar power, CSP, and compressed air energy storage in order to provide a competitive CSP plant. As you all know, CSP is currently in a crisis. You can see here the cumulative capacity installed. So we have about 8 gigawatts of CSP installed worldwide. And this is basically similar to the new PV capacity we installed yearly, for example, in Spain. For example, in 2023, we have installed 5.6 gigawatts in Spain only. And worldwide, we have in 1 year about 350 gigawatt new installed capacity, and worldwide we are now at about 1.5 terawatt installed. So you can see that the CSP sector is really small compared to PV, and also the technology is not. We don't have a reference technology, so we don't have a major CSP plant currently. So at the beginning we had parabolic trough, and now we are moving towards the central receiver concept. So we have several towers in commercial operation, but not really many plants. And for example, also a similar thing happened with storage. At the beginning, we didn't have any storage with CSP. Then we have small scale storage, then we had large scale storage. And now we can see that we have a rise of hybrid power plants. So we are combining PV, wind, and CSP in order to provide grid stability. So that's actually the point that CSP is a hybrid generation and storage technology in order to provide or to enable a large-scale integration of cheap PV and wind. And that's exactly where SOLARX is focusing. So we would like to provide grid stability and enable a high share of PV and wind energy in the power grid. And SOLARX we are having 17 partners in 10 countries in Europe. The project lasts about 4 years, and we finish in September 2027. We have a total budget of 7.2 million euros, and at the project end, we are going to reach TRL 6.7. So what the concept is explained here. So during charging, we use low-value electricity from the grid in order to compress air. At the same time, we also store high-temperature heat with the CSP part of the plant. And for heat storage, we use a thermocline stacked bed of rocks, which is really cost-effective for high-temperature heat storage. And once the grid prices are high, so during peak hours, we're going to discharge the system and take the compressed air. We're going to heat the compressed air with the stored heat from the CSP plant, and then we expand the hot compressed air in a gas expander and produce electricity. And we also would like to recover the exhaust heat as much as possible. So we could either supply process heat to industry, or also to implement the bottoming cycle to make best use of the low-value exhaust stream heat. And we could also use a bottoming cycle and process heat supply with a mix here. So, and during the project, we are going to develop several key components. For example, for charging, we have the solar receiver, which is a barometric solar receiver, which heats air up to about 800 degrees Celsius. And we're focusing on artificial intelligence-based flux control. And also we are going to develop new sensors to monitor flux. It's important to know what is actually happening at the receiver to best focus the heliostats. And we're also having tailored compressor design. And we're going to optimize also artificial pressure vessels to provide cost-effective storage of pressurized air in an artificial manner. And during discharging, we're focusing on optimized heat exchanger technology because we have air heat exchangers, and as you know, the heat transfer between air is challenging because we have a low heat transfer coefficient. So we need to optimize the heat transfer and optimize the design to provide the cost-effective solution. And we're also focusing on tailored air expanders, starting from 1 megawatt electric until about 250 megawatt, could always be larger, maybe until 200 megawatt electric. And we would also like to combine the system with automation in order to make best use of low value excess heat. And we would also like to combine the pressure storage with reverse osmosis determination to provide some storage for the determination plants. So this is all optimized and worked on in our project. And since project start, we have been focused on thermodynamic optimization of the plant concept, also techno-economic optimization, taking into account different grid boundary conditions, also different countries. Then we have been busy with solar receiver testing at small scale at the solar furnace at CIMAT PSA in the south of Spain. And we also have been busy with artificial intelligence-based tracking and role of heliostats and experiments of sensors. And towards the end of the project, we are going to optimize the concept for different use cases around the world, because as you know, the CSP part needs high ENI, so we need to have a high solar resource. And as we propose the combination with compressed air energy storage, we also need to have underground caverns available in the same areas, or if when we use artificial pressure vessels, we are not dependent on location, so we can just focus on solar resource. And so we need to optimize the concept of different locations, and also taking into account the electricity price boundary condition worldwide. And in parallel, we're going to install a small-scale KS-CSP prototype in the south of Spain, a CM@PSA. And there you can see on the right-hand side, there's more 3D view of the prototype. So you can see the solar receiver, which is going to heat the pressurized air stream in the heat exchanger in the red one you can see here. And then the pressurized air, the hot pressurized air is going to be expanded or expand in a small-scale gas expander and produces electricity. So we're going to demonstrate a small-scale KS-CSP plant in a research facility in the south of Spain. And as a pressure storage, we're going to use commercial pressure cylinders for gas storage, and they're connected here in some panels with a total volume of 4.8 cubic meters. And that's currently being integrated in the existing research facility, and testing should start in the last project year. Currently, we are busy with the work there for prototype integration. Okay, thank you. This was everything from my side. Do you have any questions?
Okay, perfect. Thank you very much, Fritz. Now we will jump directly to Christina. I will give rights.
Hello, can you hear me?
Yes, we can hear you.
Let me share the presentation. Can you see my screen? I'm not here.
Now, yes.
Now, yes. Okay. Thank you. Well, thank you for the opportunity to present the project Hybrid Plus about advanced hybrid solar plant with phase change material storage solution in supercritical CO2 cycles. The project initially had a budget of 3 million and was formed by a consortium of 7 partners, 3 universities, with the Universidad de Sevilla as coordinator, the University of Lleida and the KTH, and for SIME, Seiko, an expert in electrical heater, Build to Zero, specialized in developing product for industrial decarbonization, Stacks, which develops metallical bulls, and R2M, responsible for exploitation. We are currently signing the amendment to include a new research center as partner, Guna from Turkey, following the granting of a HOPON. In order to understand the project objectives, we will explain the evolution of the project with respect to the state of the art. A traditional concentrated solar power plant uses a Rankine power cycle. Sorry, I think I was in mute my phone. With Rankine steam power cycle, we use solar as a heat transfer fluid. The solar has a composition of 40% of potassium nitrate and 60% of sodium nitrate, with temperature up to 565 degrees due to salt degradation. And for high temperature efficiency, basically we use the plant in a central receiver configuration with a direct 2-tank solar tank storage system. But to increase the efficiency, we want to work with the Brighton supercritical CO2 power cycle. And in order to use this advanced cycle, we need to reach the working fluid temperature to around 600 degrees. The solar salt can technically operate at 600 degrees, but only for short residence times. This means that they are suitable to be used as heat transfer fluid, but not as a storage media, because the prolonged use of this HTF at high temperature will produce degradation. And for this reason, the project implements indirect thermal energy storage using a phase change material. This strategy allows us to decouple the heat transfer fluid from the storage media and enable the operation at higher temperature without compromising the material stability in the storage system. So, in addition, these phase change are selected for their availability to store a large amount of energy during phase change transition. We can use this system as an indirect configuration. So, in the use of these phase change materials in this indirect configuration, we also allow the hybridization of the storage system. So we can charge this storage thermally with the solar field of the CSP plant, or we can charge by electrification, direct electrification of this storage system with the energy produced by any other renewable energies as PV or wind, or with the excess of energy produced supplied by the grid. So basically, the core objective of the Hybrid Plus project is to demonstrate an electrified thermal energy storage system based on phase change material arranged in a cascade configuration designed for the next generation of hybrid CSP plant with advanced supercritical CO2 cycle. The cascade configuration addressed the issue of the thermal hysteresis between charging and discharging when we are working with a sensible heat transfer fluid. So if we use this multiple phase change material with progressive increasing this melting point, we can match better the variable temperature profile of the HTF during the charge and during the discharge. That's increase the round trip efficiency of this storage system and allow a more effective energy utilization and an easier integration in these supercritical CO2 cycles. So, as part of the Hybrid Plus project, we are developing and optimizing the design of this PCM storage module. This process includes the selection of suitable high-temperature PCM and the integration of a thermal conductivity enhancer, which are essential to ensure the efficient heat transfer in phase change material. And to improve this overall thermal performance, we incorporate metal balls into the PCM matrix. With this configuration, the idea is to validate this module in a new pilot plant that is under construction. So the first step in the Hybrid Plus has been the selection and characterization of the phase change material for each stage of the cascade configuration. Starting from the system requirement, we conducted a material screening, followed by a thermophysical property characterization, and a complete characterization of the composite. The composite is formed by the mixture of the PCM with the metal wool selected as composite for the storage material. So basically, this selection characterization of the PCM began with a comprehensive literature review that include commercial data sheet and numerically developed effective mixture. Then we define it a system requirement such as thermal property, compatibility cost, and stability. And later we conducted a first screening, prioritizing KPIs like safety, environmental impact, and cost. And also we performed hydroscopic spec and preliminary corrosion assessment in order to select material for the pilot plant that we are going to install we are installing at this moment in the University of Seville, and for the final concept for different application, for CFP application in power blocks, and a CSP application for the carbonization industries. In addition, we have explored different arrangement of the metal bolts. We can see here different configuration with parallel tube with bolts packaged loosely around them, a more compact tic-tac placement to increase the surface contact, and in addition, a fully filled block with no defined tube spacing in order to maximize the material density. And the mixture, we have characterized the effective conductivity of the composite. Here we can see how we prepare the material with the bolt and with the solids used as heat transfer fluid, and we have measured this thermal conductivity with a special hot disk. We have performed a thermal simulation using ANSYS Fluent to validate the performance of the PCM module arranged in the cascade configuration. The simulation results confirmed the behavior observed in earlier model developed by us in Open Modelic and MATLAB Simscape, and the key outcome was that the inclusion of the metal wool significantly improved the thermal conductivity of the storage system, and this enhancement reduced the role of the natural convection in the liquid phase, but increased the poorly conductivity in the solid phase. Here we can see also some results of the cascade configuration, how we can reach stability after the first cycles in the cascade for charge and for discharge. And finally, as I mentioned, we are going to validate this concept in a pilot plant. The pilot plant has been developed to replicate the main component of the technology. So in a CSP plant, we will have an energy sources. In the hybrid configuration, these energy sources came from the sun and came from the excess of electricity came in from other renewable energies or from the grid. We will have an energy sink that could be a power block for power applications, or steam for the carbonization in the industry. We will have a heat transfer fluid, molten salt in that case, and the new thermal energy storage, the phase change material in a cascade arrangement. And the pilot plant that we have under construction in the University of Seville will replicate all these parts. The energy sources will be or is obtained with an electrical heater by Joule effect that can heat directly the HDF, with immersion heater in the PCM modules in order to electrify the storage system directly. And we are developing also a induction heater as a secondary energy source in our pilot plant. The energy sink is an air cooler made tailor-made by us. The HDF will be the solar salt that we have commented at the beginning of this exploration. And the thermal energy storage will be the phase change material. And we have the capability to validate a single configuration, just one module, or the cascade configuration with 2 modules representing any 2 steps of the cascade arrangement. Here we can see more in detail the design evolution that we have had in the project. We have had several engineering iterations due to 2 key factors. The first was the space limitation that we have in the university. And the second one was the increasing cost of the material and equipment, taking into account that the original budget was estimated with cost of more than 4 years ago. And basically, this is the final design that we have in our plan. Here we can see the electrical heater and the PCM modules, the molten salt tank, the cooler. And if we want to see more in detail part of this component, this is the molten salt tank with a capacity of 3 square meters. We can reach at to 600 degrees, and we have 2 electrical heaters in order to cover the heat losses and also to produce a direct melting system inside the tank. Also, we can see the molten salt tank that will be installed inside the tank, the inline electrical heater to heat the HDF in a shell and tube configuration, the electrical sheet in tube, and the molten salt on the shell side. The capacity of this electrical heater is 150 kilowatts of power. And again, we can reach 600 degrees, up to 600 degrees with this equipment. Here we can see the PCM module that we will install in the pilot plant. And the idea is to start the validation with the first phase material, is sodium nitrate. We will work with a melting temperature about 310 degrees, and the molten salt will have a thermal will charge at 360 degrees. I will discharge at 290 degrees. Finally, we can see here the air cooler tailor-made by us in order to remove the excess of energy, design it to reach temperature up to 600 degrees again, and with blow it, equip it with variable speed right for partial load operation. And basically, this plant has been designed to be very flexible, to enhance the safety. All system is full drainage from the design, being the tank able to accommodate the whole inventory of the HDF. Different thermal energy storage configuration can be accommodated from temperature range from 150 degrees to 600 degrees. The modules can be replaced easily to validate different thermal energy storage configuration, different enhancing materials, and different heat. We can validate different heat exchanger electrical heater configuration, different PCM configuration, including micro and macro encapsulated solution. The idea in the future is to validate this in a direct steam generation solution for process heat. And also we can validate different HDF. Originally, we are going to work with solar salt, but we can also change this HDF for thermal salt. So the plant is under construction at this moment and will be in operation at the end of this year. Anyway, if you want to follow us in the media, you can follow us by different networks. And if you have any question, we are completely available for answering you, or you can write me by email, and with high pleasure, I will answer you as soon as possible. So thank you very much for your attention.
Thank you so much, Cristina, again, for the presentation. Very nice one. Indeed, we have a question from Jan Scarorti, and he said, thank you for a nice presentation. Have you considered differences in the dynamic behavior, different melting and freezing time of different material, of selected materials for PCM cascade? If yes, are these results published? Thank you for your answer.
Yes, this is one of the most important studies that we are carrying out. Basically, the ANSYS model that we are developing has validated this dynamic behavior, taking into account that the every PCM model will have latent heat and also will work with sensible heat. If you see the cascade, we will start in every module with sensible heat at the beginning, the front of fusion, the most part of the module, and sensible heat in the outlet. How these different three parties will evolve under dynamic behavior and at partial load is one of the key issue that we are validating. At this moment, the simulation in ANSYS, we are able to reach a stable condition even under dynamic situation. And the idea is to validate this ANSYS model with the data from the pilot plant.
Great. Thank you so much, Cristina, for the answer. Jan, we expect that she fulfilled your expectations. And now is time for the next speaker. He is Enrique Pascual. As I mentioned before, he is also part of SOLARX project, but today he's going to speak about another project called Leia. So Enrique, let's...
Yeah, thank you. I'm start sharing my screen. Yeah, it seems that is being shared. Can you see my screen and hear me properly?
Yes,
okay, good. So I will start. So first of all, good afternoon. Thank you very much for having me here. As Miriam mentioned, my name is Enrique Pascual. I'm here representing both Acciona Industrial, the research and development team of Acciona, and Leia Consortium, focusing on solar field measurement to increase performance. This project is granted by the European Commission under the CSP ARENET program. So, my talk today is divided in the following points. First, I will start introducing the project, the partners and objectives. Then I will move to the more technical activities, focusing mostly on heliostat and receiver energy control system. And finally, I will show you briefly the conceptual integration of one of the tools into the DCS, and finally I will provide you some of the main conclusions. So this consortium is formed by a very well-balanced institution ranging from the fundamental knowledge of technical centers to companies in the CSP field from both Spain and Germany. In particular, Acciona Industrial, the company I'm representing today, acts as the main end user and industrial leader of the project. Also from Spain, we have Tiware developing tools for both solar field and receiver characterization techniques. And complementing the companies from Spain, we have CENER and CIEMAT, both working on solar field receiver and heliostat control tools. Complementary from Germany, companies such as CSP Services and Siemens are also collaborating or are also part of this consortium. And finally, DLR is also involved as a research institution leading activities in the receiver characterization and soiling inspection. So the general objective of this layer project aims to cover, let's say, the few or the main relevant elements in a CSP plan, aiming to shed some light on for deeper understanding of the main elements of this CSP tower plant, including heliostat field, starting from heliostat field, then looking at the receiver, and finally looking at the control system for the potential integration. In particular, when we look at a heliostat field, we will develop some of the optical tools in order to gain some knowledge on the calibration, because this is essential to run properly CSP plan. Also developing some characterization and looking at the reflectance, because the cleaner the solar field are, the higher energy that eventually will reflect to the tower. Some of the automatic soil inspection tools are being also developed. Then moving into the receiver, we will look at different tools for the characterization of the incident to make sure that some tools can be quantitatively enough to obtain and monitor in real time the amount of energy reaching to the receiver, and also some efficiency tools. Finally, as mentioned before, we will look at a tool that integrates these signals from the heliostat field and receiver, and the conceptual integration of these tools into the DCS system. For the validation of these tools, a PSA installation and Zener installation are being used together with Cerro Dominador, which is operated and maintained by Acciona Industrial. But due to some technical issues, Gema Solar Plant was also included as part of the validation side of this project. So simply to share some numbers about the main testing side of this project. Cerro Dominador is the largest concentrated solar tower plant in Latin America. Cerro Dominador, you can see the picture in the background, has more than 10,600 heliostat with more than 140 square meters spread over 700 square hectares. These heliostat reflect sun rays up to a receiver located at the 250 meters height, as you can see here, the black cylinder in the tower, and its nominal capacity is 110 megawatt electrical megawatt, yielding to 950 gigawatt hours. And it's also very relevant that the thermal storage system is based on molten salts, the solar salt, with an equivalent of 17.5 hours of electric production without sun irradiance, which make this technology very flexible for dispatchability. Let's start looking at the tools for controlling the field, heliostat field solution. So we will have 3 different tools, and first let's look at the online heliostat characterization system developed by GEMAT. And the objective of this tool is to advance towards the state-of-the-art camera target method for heliostat calibration and characterization. The idea behind of this optical modeling analyzes simultaneously the image taken at different times, as you can see here in this image along the day, to reproduce synthetically the optical behavior of an heliostat. So after processing these images, based on multi-objective algorithm, the model can extract precisely focal length, zenithal and azimuth mirror and slope deviation. So the idea, as I mentioned before, is to gain more insight about a heliostat with respect to the typical state-of-the-art based that simply extract slope error and a slope deviation. So this tool is currently validated at PSA, but towards the end of the project, the idea is to use images extracted from Cerro Dominador plant in order to double check with real images. So then we will move to Heliostat Char Plus, the Heliostat Field Direct Characterization System. This tool is developed by CENER. This direct characterization system measures directly the reflected light with a pole feature with photosensors right vertically, as you can see here on the right-hand side image. So once the photodetectors measures the flux irradiance of an heliostat, it extracts something like this. So it's like a distribution of flux in X and Y. So far, this tool has been validated experimentally or theoretically, let's say, with a ray tracer simulator. As you can see here in the picture of the middle, the shape of the flux distribution matches very nicely with the direct measure of the Heliostar Plus system. So with this tool, the idea is to understand better the flux and the reflective flux from Heliostat, also leveraging these two as part of the commissioning of a solar field, because there is not an intensive use of the camera target state-of-the-art method. And finally, let's move to the last tool for characterizing the solar field. In this case, is the automated soiling inspection. This tool is co-developed by DLR and CSP services. Unlike the other tools, in order to gain deeper understanding of characterization, calibration of heliostat, this tool is focused on measuring the soiling and as a proxy of the reflectance. So the idea is, or this on a drone, as you can see here on the reflected image, coupled with an RGB camera. So after checking the reflectance of the mirror, it can extract or predict, let's say, the soiling loss compared to the reference samples. So when we look at soiling in compared with the measured, it shows a very good agreement between the predicted and the measure. So this tool is currently validated at the PSA, and the idea is in the next month move and validate this tool in Gemasolar plant. So now let's move to the receiver control solution. So first we have QFlux, is the contactless quantitative flux density measurement, also developed by both DLR and CSP services. So this system consists of a set of cameras installed on the solar field, similarly to those of infrared cameras pointing at the receiver. So after an initial calibration of the receiver during the night, then during the daylight and operation, and these cameras measure quantitatively the incident irradiance on the receiver. After this post-processing, this tool will serve as a good complement of infrared maps of the receiver, due to the fact that the flux changes more rapidly than the temperature that these infrared cameras are measuring. So the idea is to anticipate to any potential problem that might happen in the future, so we like more robustness of this technology. Then we are developing another tool. In this case, this high irradiance hybrid measurement is developed by the PSA from TMAT, and this system consists of a direct irradiance measurement. This device, as you can see here in the picture, is located in a closed area to the main receiver, and the idea is to leverage the spillage of the flux out of the receiver in order to use this kind of information for calibration for any visual inspection. So this kind of radiometer will serve as a reference for future estimation of the flux. Next, we will move to the contactless receiver characterization. So this tool is also developed by DLR and CSP services. So the objective of this tool, again, is to monitor the status in real time of the receiver by comparing thermographic images with visual images. This tool is being tested currently in Jülich, in Germany, and so far in infrared measurements of receiver samples have been used in order to validate experimentally at lab scale the capability of this tool. The idea behind this tool is to identify any sign of oxidation remotely at the receiver, as you can see here on the image on the right hand side. This tool will serve to extend the lifetime and to gain deeper knowledge on any effect that happen on the coating and the receiver panels. So we see this tool as a preventing quantitative tool for monitoring the status of the receiver. And finally, when we look at the final tool of the receiver characterization, is the power on-off method. So this is a very well-established method. So the idea of this activity is redefined, led by DLR. So as you might know, this experiment consists of a real experiment performed on running a CSP plant. So it consists of alternative full solar and 50% field pointed at the receiver, as you can see here, highlighted in blue squares. Blue representing 100%, and then orange square representing 50%. So after the shifting from 100% to 50%, as you can imagine, the flow mass rate of molten salt has been tuned accordingly in order to avoid any overheating or even freezing, as the number of heliostat on focus changes. So after this analysis, it will show how the receiver is behaving, and how the thermal change or thermal exchange will perform in a real operation site, and eventually it will give us some information about the efficiency of the plant. Now let's move finally to the main two blocks. So the idea of this energy management system developed by Acciona is to leverage all the information gathered from the previous sensors installed on both on the solar field and on the controlling of the heliostat. So the idea is to develop a tool that can predict what was going on in real time. So simply to give you some overview, this energy management system, we will have like the level of reflectance extracted by the drone, so all automatic drone inspection. Also, the optical quality of heliostat extracted by the different tools that we explained before, and eventually it will provide this kind of solar flux distribution on the receiver. So this is specifically a simulation for Cerro Dominador. So with these kind of maps, we will compare with those flux and measurement distribution, and we will see the kind of difference that might be coming from. So eventually we will compare. And finally, I would like to conclude this talk. The idea is to integrate each of the tools or each of the outputs of the tool into the DCS, the distributed control system of plant. So simply to give you an overview, I will share with you of the automated soiling inspection. So first, as mentioned, drone flies over the solar field, and it extracts some RGB images, and then after correlating and correcting this kind of RGB images, it can extract a calibration routine in order to have an estimated soiling or reflectance value of the solar field. And then by using the GPS positioning, it can be correlated with the heliostat ID in the solar field. So essentially, after this processing, that this kind of tool represent like the calibration and the internal post-processing that this tool has, it will share with the DCS this kind of heliostat maps in order to shed some light on the degree of soiliness of the solar plant. So essentially, after condensing all this information, the O&M manager, we will have enough information in order to plan when is the most sensitive area of the solar field, or when is the most suitable time for the cleaning, saving some time and energy resources. And finally, to conclude, we have developed several solar field methodologies in order to calibrate optically the behavior of heliostat. Some soiling inspection tool has been developed and validated experimentally. Also, we have a set of different characterization methods to explore in real time the performing of the receiver. Combining this information, we have a preliminary simulation tool that combines all of this information and predicts the behavior. And finally, I show you the conceptual integration of these tools for the future integration of them into the DCS, also assisted by the knowledge of Siemens. So with that, I would like to thank you very much for your attention.
Thanks, Enrique. Very nice presentation as well. And as we don't have any questions for now, I will give you the floor, Peter. I see that you're
Okay. I try to share my screen. I guess there's still the other screen open. You have to leave here. Now I can share mine. You should see my screen now.
Yes, we can see it, but still you need to shift, I think, to the...
Okay. Now.
That. Yes, perfect.
All right. Yeah, welcome. And I will present you now the CST for All project. In contrast to the former presentation, which were dealing with the advances of technology of CST or CSP, whatever, on the technology base here, we are talking about an coordination and support action. So CST for All tries to support any activity of CST in this area towards the set plan targets. So here we try to initiate and catalyze initiatives for hybridization and cooperation as an interface between CST and other renewable energy technologies. So we are talking here about flexible electricity, industrial process heat, and sustainable fuels. As you can see, the duration is 3 years, and we are coming to an end in end of September this year. The partners are DLR from Germany, CIEMAT from Spain, Enea from Italy, and Ertugunam from Turkey, as well as Estella from Belgium, the European Solar Thermal Electricity Association. Looking at the project objectives, as I said already, the primary goal is here to support the networks between CSP or STE, CST. You see, we have different names. So concentrated solar power, concentrated solar thermal, and solar thermal electricity. So these are the abbreviations of what we are talking normally here. So we are discussing here the network or improving the networks between the different other renewable energies and its integrated roadmaps. So all these are collaborating here in the concept of the set plan. We want to have direct cooperations between the different ATIPs, the implementation working groups, or similar stakeholder fora. We support we provide support to the existing set plan implementation plans. Of course, here with a special focus on the CSP implementation plan and advance towards a more interconnected activities. If you look here at this scheme, this shows the basis of what we are talking about when we talk about CST. All of you know that we have reflective surfaces, or we use reflective surfaces to focus and concentrate the sunlight and capture the solar radiation as heat. And this green heat can be used now for 3 different sectors: electricity, industrial process heat, and carbon neutral fuels, especially to combine CST now with low-cost thermal energy storage for greater flexibility, allow us a 24/7 production and dispatchability whenever we need it. I think this is clear to all of you that were listening to the previous presentations already. Now I explain you a little bit more about this implementation plans we are working on, especially here, the working group. The set plan countries for CST are Spain, Germany, Italy, Portugal, Turkey, Belgium, Cyprus, France, and Greece, as well as the EC. And we are assisted here with Estella as the association, and then the CSP joint program, CSP JP ERA, representing 29 organizations from research mainly, but also supported by Solar Heat Europe, EU Turbines, and others. In between of the CST project, we had one of the first targets to update the CST implementation plan. It was endorsed then in February 23. Especially it was needed because the initial targets of the project had to be adjusted. The initial targets of the implementation plan had to be adjusted to the new time frame and redefine R&I activities that were originally designed in the implementation plan, and to align these targets and related R&I activities to any new emerging energy policy context. So also we had to include the solar heat for industrial processes and solar fuels activities, which was originally, as it was a CSP implementation plan, it was not yet included there. And then there was another target to expand this implementation working group and enlarge the scope to include also non-concentrated CST. Non-concentrated, so the group of non-concentrating solar thermal agreed then to first start with the terms of reference document that was agreed between the two associations, Estella and Solar Heat Europe. It was done in January 24, and now the ball is at Solar Heat Europe to deliver their own implementation plan document. This is still ongoing or not yet terminated. And when it is available, it will be then included in this CST implementation plan. So the update of the targets in the implementation plan was 5 different ones. The first one, cost reduction of electricity provided during periods with low wind, PV and hydropower, with a cost target of 15 cents per kilowatt hour for Southern Europe locations, targeting for 2030 to around 10 cents per kilowatt hour. The second one was the development of the next generation of CSP or CST technology to achieve at least 3 points of increase of overall efficiency, which means from 39.4% to 42.4% in 2025. You see, the year has been defined in 2023, so the goal was ambitious, and it must be then prolonged because 2025 is already here, and we know that the demonstration is not yet accomplished, which brings me to the third point, the first of a kind project integrated into the energy system also by 2025. That is not yet reached, but it is scheduled and probably will be happen in 2026 or 2027, depending a lot on the financiation of such a first of a kind demonstration plant, because it's large scale and it must be then financed with a lot of money. And actually in Spain especially, there are activities going on to push for this first of a kind project. We probably hear in the next half year some news on that. And then the fourth point, the fourth target is the thermal energy cost for industrial process heat applications should come below 3 cents per kilowatt hour in 2030 for temperatures in the range of higher than 200 degrees. And the fifth target is the demonstration of a 24/7 economically viable solar thermal baseload production of green hydrogen and other solar fuels by 2030. So this is the CST implementation plan with its target. And I'm coming now to the project activities that we completed also in the meanwhile in the CST for All project. So what we were doing, we were organizing 9 different workshops to bring industry and research community together, looking at cross-sector perspectives especially, and foster public and private funding for R&I, and to create necessary political regulatory framework conditions for the execution of the IP. So we had 2 blocks. The first one was an industry workshop block. We had 6 different 5 different workshops organized here. How to combine CST with PV, to combine it with biomass, with heat pumps, geothermal and energy storage technologies. So all these workshops were basically having keynote representatives, speakers from the different industries, and bringing the technology, let's say, into the discussion and show concepts how the two technologies could then make profit of hybridization or combining the technologies. And the other second block was R&I workshops. Here we were talking and presenting mainly cross-cutting actions, for example, on material challenges for renewable energy technologies, hybridization of CST with other renewables, what R&I is necessary and what challenges do we face when we talk about hybridization. Then about meteorology for renewable energy technologies and the future mix with 100% decarbonization levels. All these 9 workshops have been already completed and were visited by a huge a number of stakeholders. We had in the order of between 70 and 150 participants in these workshops. So I would say that was a great progress here. I come to the conclusions and the overall recommendation that we took from all these different workshops, and I try to summarize that. First, about increased collaboration. Yeah, we reached out to the different research institutions, industry and policymakers, and brought them together. When it comes to material advancement, we were looking at what research and development is needed to develop more durable, sustainable and cost-effective materials for the different technologies. Then hybridization and system integration. What kind of hybrid systems should be explored and optimized and brought together for commercial projects, which then offer significant potential for enhancing the grid stability and also reducing the cost. Meteorological data and modeling is also important for all renewables. Here we were talking about how to improve the quality, accessibility and utilization of the data and models to improve and optimize site selection, forecasting or grid management. We identified a lot of necessary works on standardized testing. The policy support was very much addressed by many of our stakeholders. What targeted policies and financial incentives are really necessary to overcome the barriers for the deployment of renewable energy technologies. This is basically valid for almost all renewables, but particularly for CST, because CST got a little bit out of the focus of the policy because of the broad deployment of PV and wind especially. But when it comes to storage and dispatchability, then CST is playing a role and will play in the future a more important role even. The focus on thermal storage, I was mentioning that to increase flexibility and dispatchability of renewable energy systems, particularly for industrial heat applications now, and the market support, how to create supply chains that are necessary, especially in Europe when you look into the competition, especially when you look at PV with the Chinese production and look at the European market where almost all our industry has disappeared, and we are fighting now with the new EC strategies to bring back industry to Europe, especially when it comes to CSP or CST, where Europe is still in a almost leading position. You know that the Chinese market is actually booming also on CST and CSP. So Europe has to make a great effort to guarantee the supply chain of the materials and create a local market. And last but not least, circularity is also, let's say, a topic or an action that has to be improved to reduce waste and critical material usage, especially when it comes to hybridization options. And last but not least, I want to show also another aspect, which is the social science and humanities activities that we took over in CST for All to look a little bit further with some surveys that we accomplished in all these different workshops to ask our stakeholders about the cross-sectional collaboration, technology adoption, societal transformation, public support, social acceptance, and gender inclusion, and develop the strategies how to solve the Green Deal challenges to boost the networking and communication, and how to exploit SSH contributions to overcome the challenges in main policy documents and action plans. That was also an important activity here. And last but not least, I want to show you here your contact options where you can contact us and ask you to be informed also on our late or final event that we will have in September, probably the second week in September in Brussels, where we conclude the CST for All activities in a workshop. With this, thank you very much for your attention.
Thank you, Peter, for closing the webinar with these words, because in the end, this was the main aim of this webinar, because we designed it as a clustering activity. So many thanks for summarizing all these insights and trying to enhance this visibility that we want to give as well to the ecosystem around CSP and all the technology that you are all working on. So thank you very much, everyone. Nicole already went because we are a little bit late on time, but I wanted to mention all of you that the recording of the full webinar will be available soon, and also from the SOLARX project we will consider some of the inputs that we receive and so on, and we will be in touch with you for next actions that we want to implement collaboratively. So many thanks, and enjoy the rest of the day.
Thank you.
Thank you.
And bye-bye.
Everybody. Bye-bye.
Bye-bye.
Yeah.
Thank you very much.